Welcome to another deep dive. We're diving into the world of quantum gravimeters today.
Sounds pretty complex.
It is, but also fascinating. Our guide for this deep dive is an essay by Yurgoi Schneepat.
Ah, okay.
So have you ever thought about, measuring gravity with atoms?
With atoms?
Yeah, that's what these quantum gravimeters can do.
Interesting. I mean, I know gravity keeps us on the ground, but why measure it so precisely? What's the point?
Well, to get started, maybe we should quickly explain what a gravimeter is.
Yeah, good.
What it actually does.
Right. So at its simplest, a gravimeter measures the strength of gravity at a specific spot.
Okay.
And, we've had gravimeters for a while now, traditional ones, often using springs or pendulums.
Right, the mechanical kind.
Exactly, yeah. They're good for general measurements, but quantum gravimeters, they offer a whole new level of sensitivity.
So way more precise.
Yeah, we're talking about detecting tiny changes in gravity, changes that could reveal things like underground structures or variations in the Earth's density.
Wow, so we can actually see what's hidden beneath the surface.
Exactly.
That's amazing. But how do they work? Is it really just about dropping atoms and seeing how fast they fall?
Well, it's a bit more complicated than that. Quantum gravimeters actually use some of the most mind-bending principles of quantum mechanics.
Uh-oh, quantum mechanics.
Specifically, things like superposition and interference.
Okay, you're going to have to break those down for me. Those are some serious brain-twisting concepts.
Sure. Let's start with superposition. Imagine an atom can exist in multiple states at the same time.
Multiple states at the same time. Okay.
Yeah, kind of like a spinning coin before it lands.
I see, so it's both heads and tails at the same time.
Exactly, until you actually look at it and it settles on one.
Right.
In the quantum world, particles like atoms can be in multiple states until we try to measure them.
Okay, I think I'm getting that. But what about interference? How does that play into all of this?
So imagine these atoms existing in their multiple states as waves spreading out.
Okay, like ripples.
Right. And when those waves come back together, they create a pattern of interference.
Like when ripples in a pond intersect.
Exactly. And by looking at this interference pattern, we can get really precise information about the gravitational field those atoms went through.
So it's not just how fast they fall, it's how their, quantum waves are affected by gravity.
Precisely. And that's where the real magic happens. This process, called atom interferometry, allows us to create these incredibly sensitive gravity sensors.
So walk us through it. What are the steps to make one of these quantum gravimeters work?
All right. First, you have to cool the atoms down to almost absolute zero.
Wow, that's cold.
Yeah, we use lasers for that. And at these super low temperatures, the atoms get really slow and their quantum behavior becomes more pronounced.
It's just like slowing down a hummingbird so you can actually see its wings move.
Yeah, a good analogy.
So we're essentially freezing these atoms to make them more sensitive to gravity. What's next?
Well, once we've got these super cooled atoms, we need to trap them.
Okay, how do we do that?
Using a combination of magnets and lasers, it's called a magneto-optical trap.
So that's the quantum gravimeter part.
Not quite yet. That's just the starting point. Now we've got our super cooled atoms all trapped and ready to go.
Okay, I'm intrigued. What's the next step?
This is where the Ramsey-Bourdais interferometer comes in.
Oh, that sounds complicated.
It uses these really precisely timed pulses of laser light to manipulate those trapped atoms. We split them into two groups and send them on different paths.
Like an atomic obstacle course.
Exactly. And as they move along these different paths, they experience the subtle variations in gravity differently.
I see.
Then when those groups are brought back together, their interference pattern, the way their waves combine, it tells us a lot about the gravitational field they just traveled through.
It's amazing how we can use these quantum phenomena to create such sensitive instruments. So what makes quantum gravimeters so much better than the traditional ones?
Well, for one, the accuracy is incredible.
Okay, so they're more accurate.
Much more accurate. They can detect tiny variations in gravity that traditional mechanical gravimeters would miss entirely. And this opens up so many possibilities. For example, mapping the Earth's subsurface in detail, or even guiding spacecraft with much greater precision.
So it's not just a small improvement, it's a whole new level of precision.
Exactly. And it's not just accuracy. They also have amazing long-term stability.
What do you mean?
Well, they're much less prone to things like mechanical drift, wear and tear over time, and external disturbances.
Ah, so they're not only more precise, but they stay precise for much longer.
Precisely. It's like comparing a hand-drawn map to a GPS system.
A huge difference.
The quantum gravimeter gives us a level of reliability and consistency that just wasn't possible before.
This is fascinating. Now I'm really curious to hear more about those applications.
Yeah, let's dive into that.
You mentioned geophysics. Can you tell me more about that?
Sure. Imagine being able to map the Earth's subsurface with incredible detail.
Okay, so like a 3D map of what's underground?
Yeah, think of it like X-ray vision for the Earth. We could see things like hidden underground cavities, pinpoint mineral deposits, and even monitor volcanic activity for potential eruptions.
That's amazing. It sounds like it would be incredibly valuable for so many things, from resource exploration to, like, disaster preparedness.
Absolutely. And speaking of resource exploration, quantum gravimeters could be game changers for finding water, especially in areas dealing with drought or water scarcity.
Wow.
They could also help us locate those rare earth minerals that are crucial for modern technology.
So these quantum gravimeters could actually help create a more sustainable future.
Definitely a possibility. And it goes beyond just Earth. What about space exploration?
Okay, that's exciting. How could they be used in space?
Well, imagine using them to guide spacecraft with incredible precision around planets and moons.
Wow.
We could unlock the secrets of planetary interiors and even conduct experiments to test fundamental physics in the unique environment of space.
So these tiny atoms could revolutionize our understanding of the cosmos.
Absolutely.
That's incredible. But before we get too carried away with all the possibilities, are there any challenges with this technology? I mean, it all sounds very complex.
You're right, there are some big challenges. One of the biggest is miniaturization. Right now, these instruments are bulky and require specialized lab environments. But imagine a future where we have portable, handheld quantum gravimeters.
Like something you could take out into the field.
Exactly. That would open up a whole new world of applications.
That would be incredible. And what about cost? These things probably aren't cheap to build.
You're right, cost is a major challenge. Currently, the technology is pretty expensive, which limits its accessibility.
So making it more affordable is key to realizing its full potential.
Absolutely.
But what about integration? Can these things work with our existing systems?
That's a crucial point. Integrating quantum gravimeters with current infrastructure and data systems is essential. Imagine real-time monitoring of things like pipelines or power grids using networks of these sensors. But to make that happen, we need to make sure the data they collect can be easily shared and analyzed.
So it's not just about building the technology, but making sure it can work within our existing systems.
Exactly. It's a multifaceted challenge.
This has been an amazing journey so far. We've gone from basic gravity to quantum mechanics, and now we're talking about applications that could change how we understand our planet, explore space, and even impact national security.
And we're just scratching the surface. The potential of quantum gravimeters is vast and continues to unfold.
Well, let's take a moment to process all this incredible information before we dive further into the amazing applications of quantum gravimeters. All right, so we've talked about how these quantum gravimeters work and why they're so revolutionary.
Right.
But we only touched on a few of their potential applications.
Yeah, there's a lot more to explore.
What are some other areas where this technology could really make a difference?
Well, we briefly talked about national security.
Right.
It's fascinating how this technology, coming from these fundamental principles of physics, can have such direct implications for security and defense.
It is pretty amazing. Can you give us some more details about those applications?
Sure. One area where quantum gravimeters could be really valuable is in detecting underground structures.
Okay.
Imagine pinpointing the location of hidden tunnels or bunkers with incredible precision.
Wow.
That's something this technology could enable.
That's pretty amazing. It sounds like something straight out of a spy movie.
Right.
What other security applications are there?
Well, another area that's being explored is submarine navigation.
Using quantum gravimeters.
Yeah, they could allow submarines to navigate with, unprecedented accuracy.
I see.
Even in the deepest parts of the ocean where GPS signals can't reach.
So we're talking about everything from managing resources and scientific exploration to national security. The range of applications is really impressive.
It is.
But, as you mentioned earlier, there are still some challenges.
Yeah, definitely.
What are researchers working on right now to make this technology even better, more powerful, and more accessible?
Oh, miniaturization is a big one.
Right, you mentioned that before.
As I said, right now, these instruments are often quite large and need these specialized environments.
Yeah.
But researchers are trying to develop portable, handheld, quantum gravimeters.
So you could just take them out into the field.
Exactly. That would be a game changer.
Imagine geologists using these devices to map underground formations in remote locations.
Yeah.
Or engineers using them to monitor the stability of bridges and buildings in real time.
Exactly.
That would be incredible.
Well, possibilities are endless.
What about cost? Any breakthroughs on the horizon that could make this technology more affordable?
Researchers are always exploring new materials and manufacturing techniques to bring down the cost.
Okay.
As the technology gets more advanced and production scales up, we can expect quantum gravimeters to become more affordable.
That makes sense.
And that'll make them accessible to a wider range of industries and applications.
It sounds like there's a real push to get this technology out of the lab and into the real world.
There is.
But what about integration? How do we make sure this technology can work with all our existing systems?
That's a great point. Integration is crucial. Imagine the potential for real-time monitoring of things like pipelines or power grids.
Okay.
Using networks of these sensors. But for that to work, we need to make sure the data they collect can be shared, analyzed, and acted upon easily.
So it's not enough to have the technology we have to make sure it can communicate effectively with our current systems.
Exactly.
This has been such a fascinating deep dive. We've covered so much. From the basic principles of gravity and quantum mechanics to the groundbreaking applications of quantum gravimeters. It's amazing how this technology, based on the bizarre world of atoms, could have such a profound impact on our lives.
It really is remarkable, and we're only just beginning to scratch the surface. As research continues and the technology develops, we'll definitely discover new and innovative ways to harness its power.
Well, before we wrap up our deep dive into this incredible world of quantum gravimeters, let's take a moment to think about what we've learned. So after this incredible journey into quantum gravimeters, what's the one thing you really want our listeners to take away from this?
I think it's appreciating the interconnectedness of scientific knowledge. Like, we began with these kind of abstract theories of gravity and quantum mechanics, and now we're using them to build devices that can see through the Earth, even guide us through space.
It's amazing, right?
It really highlights the power of basic research.
Yeah.
How it can lead to these unbelievable technological leaps forward.
Yeah. It's like Yurgo Schneppot, whose essay kind of inspired this whole deep dive, said, we're on the verge of a new era in sensing and measurement.
Absolutely. And that kind of brings me to a final thought for our listeners. We've talked about all these applications, right? Geophysics, exploration, navigation, security. But what other uses can you think of for this technology? What possibilities are we maybe missing? It's a question worth thinking about.
That's a great point. Sometimes the biggest breakthroughs come from asking what if and looking at things from a whole new angle. So, to everyone listening, keep those creative sparks going. Thanks for joining us on this deep dive into the fascinating world of quantum gravimeters. Until next time, keep exploring, keep questioning, and keep diving deep.